And in fact, some people could explore their own IP layer this week. You probably heard in the news about the problem at Facebook, where the network was down for quite a long period of time. It's not clear yet to the outside what really happened, but what you can read from Facebook itself is that they were using something like SDN, software-defined networking, that we will study briefly in a few more weeks, where essentially a computer is able to control the routing tables that's in the different routers. And then guess what? If you send wrong commands to the routers, then you cannot talk to the routers anymore. So that seems to have been the root of the problem. We solved this problem by having VirtualBox and Mininet, where you can still, if you do anything wrong, you can still, through software, get into it. Software-defined networking is the same idea, except if you really do things badly in the routing tables in particular, then it's no longer possible to talk to the routers, so it's impossible to control them remotely. And because of security, the people who were local, who had physical access to the machines, could not control them. And the people who could control them did not have access to the machine. So it took a long time. They had, as I understand, to ship people physically to places to fix the problem. The problem was compounded by other things, as we read, DNS and BGP. We'll talk about that. So it seems that in addition, the DNS of Facebook was down, and probably they were also using very short time to leave records in the DNS, which means that if you wanted to access a machine by its name, it did not work, which of course made the debugging more difficult because you had to use the addresses. Now, if they use IPv6 addresses, then you can imagine the nightmare it was to typing all those addresses to get things right. And as you can see, Facebook is hiring lots of routing and data path engineers. So they will probably fix the problem in the future. So we'll talk about that when we talk. Some of those things will become clear when we talk about BGP and DNS, we've already mentioned, and SDN. Right now, we're continuing our exploration of the very basics of the IP layer, and we finished with NATs last week. And we saw that what a NAT does is modify the local port numbers that are assigned on the local part of it, on its local face, modifies them by, which in principle is forbidden because it's transport layer, but we do it. And this allows to reuse the physical address that's given to the NAT among multiple devices here. We've seen this, and the issue is, of course, when we have a server on the NATs, on the local part of the NAT, this does not work automatically because the port number here, the NAT maintains its table on the fly by observing the traffic, by spying on all the traffic. We'll see that many devices do that, bridges do the same. And this is making the assumption that you contact a server to the outside, therefore you discover the local port number. But if a server is here, the first message of communication can come from the outside, and this will not work. So peer-to-peer applications like Skype or some initial versions of Skype did not work well with the very, very first version did not work well with NATs. And one of the success of Skype was, in fact, to solve this NAT problem automatically. So now all peer-to-peer applications know how to do it. But if you have a true server here, that is not a peer-to-peer, but a true server here, you need to configure that manually, as we talked about it last week. NATs were invented to solve a problem of IPv4. IPv4 does not have enough addresses to be able to give 20 addresses to every home, for example. It's even hard to get one today. So that was the problem that motivated NATs. But it turns out that, so therefore, if with IPv6, very often we will not use NATs, or we'll still have a box that people can call a NAT, or your ADSL modem, or your home router. With IPv6, typically in Switzerland, what you have is that your provider will give to you not one address, but a prefix. For example, here, a prefix of 60 bits. That means I have for my home network all this prefix here. So my internet service providers will forward to me anything that corresponds to this prefix, which means that I can use a part of this to have many hosts in my own network. And this is easy with IPv6 because the IPv6 address is so long. We can have first receive lots of addresses, and second, we will be able to use many of them in our local network. So we can have a fairly large size local network with IPv6, at least in theory. And this theory is also practical for example, the big ISPs of Switzerland. This is how they provide things here. However, there is still an issue that the NAT, in fact, if you look at the previous slide, we can see that as a problem. I mean, having a server at home requires some manipulation of my home router, my ADSL access box. But in fact, it's also a protection, because that means that if I have a server at home and I have not put it here, then nobody will be able to reach it. So by default, when we use NATs, in fact, all the servers that are behind the NAT are protected. People need to know exactly what's the port number, and they cannot send traffic if they don't know exactly the port number and the address. So you cannot do discovery, and you cannot have, for example, if you have ports that are open on your computer, simply because by default configuration, perhaps the telnet port, server port is open, then probably if that is the case, you will not configure it in your NAT. Therefore, people will not be able to exploit the vulnerability of your host, which has port numbers that are open, server port numbers that are open unintentionally. So that's a filtering and protection mechanism that did not come as an intention at the beginning, but is present today with IPv4 NATs. With IPv6, typically you will do the same in the sense that an IPv6 router will act as a filtering router. It will allow communication from the outside only if initiated from the inside, unless manually configured. That means that an IPv6 router that's a home router will do more than what I presented last week, which is when a packet comes, look up the table, do longest prefix match. It will do more. It will do all the things that a NAT did, which is, do I accept this packet to this port number? And I will accept it if I have seen already in my table a request coming from inside. If B goes to a server somewhere and uses a local port number, the home router will see that and keep it in its whitelist table. It's like a NAT table. Now it's called a whitelist table. When a reply will come from the server, the home router knows, oh, it is on my whitelist. I have seen a request coming from a host here. So this is the concept of what we call a filtering routers. All routers today, in fact, except the very basic ones we use in the lab, for example, when we don't configure them for filtering, but all routers tend to have some filtering functions where they don't do automatically the function that they should do. They ask themselves whether I am allowed to do it. And here, they will not allow packets to come to a port here that is not previously seen in a packet coming from the reverse direction here, except if you configure it manually. So we keep the same property that we had with IPv4. Not all IPv6 systems work in this way, and although originally the idea of IPv6 is that NATs would be completely useless, therefore there would be no NAT for IPv6. In reality, as usual, things are more complex, and there are still NATs for IPv6. In the lab, when we use VirtualBox, then we have only one IPv6 address from our physical machine, and we have to share this IPv6 address between all the hosts that are in our virtual environment. Therefore, here, the only solution is to do NAT, because EPFL doesn't give us, we're already happy if we have one IPv6 address from EPFL. EPFL does not give us an entire prefix like a regular provider would do. So NAT still exists with IPv6, and then you have to discover when you have IPv6 at home. For some providers, perhaps they will also set up your home router to act as a NAT or as a filtering router. What I presented is a small size NAT. A small size NAT is a NAT that use one IP address. But you can trivially extend that to not one IP address, but a block of IP addresses. For example, this is what EPFL does. When you're in the private part of EPFL, you receive 10.something addresses, which you may remember are private addresses. In fact, if you do a trace routes through some routers, you will see that all the IP addresses that are given inside EPFL are 10.something addresses here. And the way this is done is that there is a big NAT that interfaces the rest of the world to this private part of EPFL. This big NAT is called a carrier-grade NAT. Carrier-grade means it is a type of NAT that is able to work for a big environment. A carrier means ISP, an internet service provider. So it will share not one address, but a number of addresses, which is still small compared to the number of users. For example, EPFL shares this block 128.178.15/24, so 256 addresses. It shares it to all the users of the VPN here. So if you appear as this address in the EPFL network, well, to the external, to the rest of the world, you will appear as that an address of this type here. And the same principle is used. We use the port numbers to be able to distinguish multiple users that may be using the same address. Of course, there's typically more than 256 users in the VPN. We multiply by a very large number, perhaps 1,000, to be able, thanks to this trick here. Also, as a consequence, you will see that NATs can be cascaded. You can be behind a NAT at home, accessing the EPFL VPN. And then when you go to the rest of EPFL, you will be inside another NAT. Worse, you could put VirtualBox in your PC at home, where a guest operating system will be behind the NAT. In that case, you will have 3 NATs between the guest operating system and the rest of the world. And then if you talk to another server somewhere, perhaps it is behind a number of NATs. So this combines very well. There is no problem with that. And this is commonly done. Carrier-grade NAT of EPFL uses 10.something addresses. When it's done by an internet service provider, as I discussed last week, it is allowed to use a specific block, the 164/10, which is reserved for carriers. So some carriers will do the same. For example, if an operator has only a small number of IPv4 addresses or fewer IPv4 addresses than it has customers, that's a way we can expand the number of users and have more customers than we have IPv4 addresses. That's one way to expand the lifetime of IPv4. And this is why IPv6 is so poorly served. This is why at EPFL we have a hard time getting IPv6 server, is because there's a number of tricks, primarily NATs, that are able to solve the problem that was initially motivating the presence of IPv6, namely the number of available addresses. NATs are a bit more complicated than what I said. For example, not all traffic uses UDP or TCP, practically all, but there is another class of traffic that we will see in a few more minutes that uses ICMP. ICMP does not have port numbers. It doesn't use UDP or TCP. This is the control and error messaging protocol of the IP layer. So a NAT must do something special for this, otherwise the ICMP messages will not work. So some NATs do not handle ICMP messages well. ICMP is used when you do ping or trace route, for example. So if you have a NAT that does not carry ICMP, doesn't handle ICMP messages well, then ping or trace route will not work through the NAT. Most NATs do it, but some VirtualBox versions do not do it well. So here you still need to find a replacement for the port numbers. So in ICMP, there is always typically an identifier of the thing we're sending. For example, when we do ping, we send a message to our machine saying, I would like an echo from you, and there is an identifier of this request here, so which takes the role of the port number. So the NAT must understand ping and other ICMP messages to be able to replace that in its NAT table. Also, some NATs are not all the same, so some NATs are easily predictable. Some other NATs are not easily predictable. A predictable NAT is one where if you connect once to a server, it's important for peer-to-peer application, or if you want to connect to a server by trying to guess this number, if it's guessable, then some applications like Teredo, for example, which uses something similar, will work well, but other applications will not work well. So that's all the difficulty of Teredo. Teredo, when it goes via NAT, it needs to make assumptions that communication in the reverse direction will use the same mapping. It's not necessarily client server, but all IPv6 traffic carried by Teredo. And this does not always work and requires some external servers. Voilà, that's all we will discuss on that. But in the lab, you will be able to experiment with them. A quick recap in the form of a question here. When a NAT has a packet to forward and an association exists in its NAT table, if an association doesn't exist, then it will make one if it's coming from the inside. If it's coming from the outside, it will drop the packet. What will the NAT do? Look for a longest prefix match or an exact match, or none of these. I'll close the poll in a few seconds. And the majority says B, which is the correct answer. Because the table now contains the port number, which has no physical meaning. It's not because you port that much that you come on the northbound interface or the southbound interface. So the combination of the IP address and the port number now is a unique identifier of a given machine at a given point in time. So it needs to do an exact match in the table, which means if we have carrier grade NATs, that of course those are machines that are limited in scale. You cannot solve the whole problem of IPv4 by having carrier grade NATs. You need to have machines that must be able to look up exactly in a table for every packet that comes. There is hardware assistance to do that, but it comes at a cost. Yes?
When we talk here about forwarding, does that only mean from the exterior to the interior, or also the other way around? Because if I'm in the NAT and I cannot connect it, the NAT will still try to do non-speaker connection.
Probably yes, in some sense, yes. Going to the exterior, here I'm assuming implicitly, I guess, that the NAT has only one connection to the exterior, so it has a default route. You do the longest prefix match if you want. Yeah, true. Yet another question. The NAT receives a packet from WAN to LAN. Here I say WAN, wide area network, to LAN, local area network. That's a terminology that's often used in the context of NATs. I think a preferable technology would be the local, the internal part of the NAT versus the external. Because when we have, for example, a NAT in VirtualBox, well, everything is local. There is not a WAN. But that's a terminology that's often used because it comes from the original development of NATs. So when a packet comes from a server that's outside and it goes inside, what is the NAT expected to modify? I close the poll in a few seconds. closing. The majority says B, which is the correct answer. The server here will send to a port number, which is not necessarily the port number as seen by A, because remember, the NAT may have changed it because A and B might have the same port number. And therefore, the port number, in fact, combined with this, identifies that this is A versus B and which port on A. So it is possible and generally expected that the destination port will be changed going to A. And of course, in the reverse direction, it's the source port number that will be changed. Without further ado, we move on to the next topic, MAC address versus IP address. That's one topic that was alluded briefly 2 weeks ago when somebody asked the question. When we go to a server, to a machine that we call by name, then we must go to DNS. And this is what broke at Facebook, that made the failure even more complicated. How about the MAC address? We've seen that when an IP packet has to be sent by a host or by a router, it needs to be sent to a destination MAC address, which is the next hop, which is the next router or the final destination if both systems are in the same local area network, if both systems are on link. Now the question is, how does a system get those MAC addresses of destinations? Of course, your own MAC addresses, you do ifconfig or ipconfig, and you'll have all the information of what are the MAC addresses that go together with your interfaces. But if you have to send to B, so you are A, you want to send to B, you need to know the MAC address of B. That's the principle of IP. IP is the inter-local area network protocol, in fact. How is it done? Well, there are multiple ways. We'll discuss alternatives, but the default approach, which is massively the one that's used practically everywhere, is to send a packet called an address resolution packet on the local area network, and all hosts that have the IP address of B, and with variants, whether it's IPv6 or not, will reply with their own MAC address. So essentially, we shout. Computer A will say, who has the IP address B? And B, hopefully, will hear it. If B doesn't hear, well, there's no point trying to send a packet to B. That means B is not online. And hopefully, no one else than B will reply. So in detail, this is how it's done with IPv6. With IPv6 and IPv4, it's quasi exactly the same, but all the terminology is different. So all the details are different, but the principles are exactly the same. That's one embarrassment with IPv6 versus IPv4. Once you understand how it works with one, you still need to know what are the acronym changes with the other one. With IPv6, it's called NDP. It's part of the Neighbor Discovery Protocol, which is part of ICMP. So remember, ICMP is the set of packets that have to do with managing the IP layer itself. And inside ICMP, there's a number of query response systems that are defined. NDP is one. It's called the Neighbor Discovery Protocol. So when A has a packet to send to the IP address of B, which is this one, for example. This is the IP address of B, F6611, and then a long EPFL prefix that we see here. So A knows B's address, perhaps through the DNS, perhaps by going through some other means. Now, A needs first to know whether I really need to send to B or to an intermediate systems that is a router. So A does the subnet mask test by analyzing whether the subnet mask of B, applying the mask to the destination B, to my address gives the same prefix. And here it's the same because it's 1A61, which is probably 1A6 is a TPFL, the part that is used for the subnet. And the beginning is the same. So the subnet prefix is all that part. It is on the same subnet. Therefore, I must send directly to B. I must now have B's MAC address. How do I get it? Well, I send a packet that is called a neighbor solicitation, NS, which is an ICMP packet that contains the question, who has IP address B? Now, so far it could be, it is simple. Now, to which IP address should we send this packet? Yes?
All router node to FS02.
Or routers. B is not necessarily a router in this case.
All nodes.
To all nodes, yeah. So by default, yeah, that's what we should do. And that's what is done in IPv4. We should broadcast to all nodes. This is not what is done in IPv6 for some reasons that committees must know. It's not entirely clear whether it's a good or a bad idea. We don't send it to everyone. It comes probably from a dogmatic point that we want to avoid broadcasts as much as possible. We want to avoid broadcasts by all means if possible. So instead of that, we do something that looks like a religious change to something. We just change the names. At the end, we do the same, but we pretend we don't do the same. It's what people do in some churches. They pretend they do one and they do the other, but they put the appropriate name on one to make it look not the same. Here, what we do is we create something which is called a multicast address, which serves only the purpose of identifying the machines that have B's address. It's very contorted, right? The people who did that were really special, right there. So you take, how does it work? You take the IP address, the target destination address, which is this one, and you take only the last 24 bits. So the last 6 hexadecimal digits, B2, the now 1, you remember the convention of compression of IPv6. When there is a 1 alone, it means in fact there are 4 hexadecimal digits, which are 3 zeros followed by a 1. So the last 24 bits, which are the last 6 digits, are 66001. So we will send this, we take this, and we take this prefix, which is a well-known prefix that is fixed. It starts by FF, so it's multicast. FF02 means it's local scope, local area. And this prefix here is always the same, and that means this is the group of all machines that have an IPv6 address with the last 24 bits equal to 661. So if someone else in the world, somewhere else, has exactly the last 24 bits, it belongs to that group only, also. But of course, it will never receive this message because this message is local area only. It is not routed. The scope of this message, it's a multicast message that can be received only by systems in the same local area. Routers will not forward this message. The beginning, the prefix FF02 contains one of the bits here that says it is of local scope. So presumably, if things are as they should be, there's only one machine that will receive it, except if by accident, there are several machines that have the same ending 24 bits, which is not entirely impossible, in which case several machines will receive it. Only the one that presumably has the same address as B will reply. So second step, B replies it. So any IPv6 host must know what is the solicited node multicast address, so it can construct it automatically by knowing its IP addresses, and has to listen to all the messages sent to this multicast group. In IPv6, there's no broadcast. We never broadcast things in IPv6. We always send to a multicast group. We will see when we talk about MAC layers that the IPv6 multicasts are sent at the MAC layer as broadcasts. This is why I say this is pure religion. You just put the right name on it, and it looks like you've solved the problem. But perhaps in the future, there will be no MAC layer. There will be only IPv6 routers, and they will understand multicast, and then there will be truly no broadcast. But this is a future that may or may not happen. So B, if B is well configured, we'll see, oh, I belong to these groups, therefore I should receive it. And I will reply. Somebody's looking for my MAC address. B, of course, knows its MAC address, sends an ICMP message with the MAC address. It's called a neighbor advertisement. And now A has obtained the MAC address. It has it in 2 ways. It has by the source MAC field in the Ethernet header, and it has it also in the reply here by looking at the content of the ICMP message. So it will know now what is the MAC address of B. Of course, you don't do that for every packet you have to send. You cache the result of this. So you keep in what is called an ARP table. It's called ARP or NDP table, depending on the ARP is the old term of IPv4. NDP is the a neighbor table in IPv6. It will keep in the cache, and whenever A has another packet to send to B, it will use the value in the cache. And the value of the cache will be refreshed, so the cache comes with a timer. If there is no activity after some time, for example, 20 minutes in some systems, the cache expires and we do this reply request exchange again. But of course, if there is proof of activity, proof that this binding of the IP address with the MAC address is still valid, then you will reset the timer. So for example, if A and B are actively talking, whenever B sends a packet to A can look at the source MAC address, look in its ARP table, will say, oh, it's the same, so it's still valid. I reset the timer. And therefore, if they talk at least once every 20 minutes, then there will never be again this exchange that will happen. I mentioned the solicited node multicast address. This is how it's done. So we take the target address. Here I remove the compression, so that's the real expansion of the address. We take the last 6 hexadecimal digit and we add this well-known prefix, which gives us this address here. In uncompressed form, this is the form of this solicited node multicast address here. If we do Wireshark, we will see such a packet. So here we see the Ethernet header. This is a packet that is sent from A to B. We see that the destination will be of this type. We'll come back to it. This is a multicast destination address that captures the end of the IP destination address. At the IP layer, we see that the destination address is this one. That's the multicast, solicited node multicast address. Here we're trying to acquire the address that ends in C01. So the last 6 hexadecimal digits are here. It gives 011. Sorry, it should be C01. And no, sorry, we're trying to acquire the address that ends in 011, correct? So the solicited node multicast address ends in 011. And the 011 is exactly what we will see also in the MAC address. We'll come back to that when we see how multicast MAC addresses are handled. And then inside IP, we will see a protocol type, which for IPv6 is called next header, that will say ICMP. So there should be somehow next header 5.8 means this is ICMP. ICMP is not UDP and not TCP. That's directly put in IP packet. And it contains a code that says this is a question for a MAC address, an NS question. And the target address is this one. In IPv4, it's in practice the same, but all the details are different. The terminology is different. It's called ARP, Address Resolution Protocol. In fact, many people, when they speak of IPv6, will continue to say ARP. So in IPv6, it's NDP-NS/NA, which admittedly is less easy to use than ARP request, ARP reply. The difference also is that the ARP request is broadcast. We don't use this complicated or contorted multicast, solicited node multicast address. And another difference is that the ARP packets are not IP packets. That's a weird thing. ARP questions, which refer to the IP layer, it makes a lot of sense, as IPv6 does, to consider those are ICMP packets, because ICMP is everything that has to do with the management of the IP layer. Here, it's a non-IP protocol. It's a protocol of its own. So seen by Ethernet, it is at the same level as IP. So there's an Ether type for ARP. And the reason for that is because when ARP was done in 1970 something, IP was one of the protocols. In fact, it was perhaps one of the most confidential protocols. The protocols that were used on local area networks were things like AppleTalk, NetWare, Novel Network, DECnet, IBM SNA, etc. Each of those had the necessity of doing an address resolution. So you could do ARP for protocols other than IP. So this is why it was treated as a non-IP protocol. Now, of course, there is only IP left, so that seems weird. So if we do the Wireshark of an ARP packet, we will see an Ethernet packet with a destination which is all ones. Now we see it's a true broadcast. Of course, this broadcast is local area in scope. It will never be carried along away by routers. It will stay in the local area network. And then the type is 0806. That's a protocol type. It's not the type for IP. It's a type for ARP. So inside the Ethernet, there is the ARP text, which mentions that the protocol type is IP, which means we're doing an ARP for IP. And IP means here in this context IPv4, and otherwise similar things. We see that the target IP address, that's the only important thing, is given here. And the target MAC address is put to 0 because it's not used, or because we don't know it. And in the reply, it will be populated. Voilà, this is the very first basic stuff about ARP, address resolution. Small poll to check your understanding. Here I'm assuming M1, where is M1? M1 is here, machine M1, sends a packet to M3. And it's the first time. M1 has rebooted, so all its ARP caches are empty. For which, what will M1 do in terms of ARP or network discovery? Yes?
This is the first packet and one sensor to or the first packet to M3?
Is the first, so M1 has just rebooted. Yeah. I close in a few seconds. And the majority says B, which is the correct answer. Here, of course, the only trick is to discover that the next hop for this communication is the router. Here, an Ethernet concentrator is a bridge or a switch. Those are all synonyms. So M1 and M3 are not in the same subnet. So M1 must send to the router. Therefore, it must find the MAC address of the router. So we'll send an ARP to P.1, and hopefully we'll get back the reply M9. Yes?
I have a question regarding the solicited node multicast request, I think it was. Why do we use that? It's like, so for example, on the ARP protocol, it's a broadcasting kind of message that's sent out. And we have the same kind of thing in NDP with the all nodes multicast. Why do you use the solicited node multicast? And what exactly is the difference between them? I tried to read up on this, but it's a bit confusing. Both of them broadcast, but I think the solicited node expects only one answer.
Okay, so the question now is not on this, but this question is about why does IPv6 send this to this address, solicited node multicast address, and not to a broadcast address, which could be all nodes in local area, which exists. That's an address that exists in IPv6. And in IPv4, that's what we do. We send to all interfaces that are in the same local area network will receive this message. Right? So all Ethernet adapters in IPv4 will receive the ARP reply. We'll see, oh, that's not for me, and we'll delete it. So the motivation is exactly what based on what I said. All Ethernet adapters receive the reply, and only when they look up at their own configuration, they'll decide, oh, it's not for me, but they've already received it. The hardware has already received. So you delete, so you receive and then delete. And the desire in IPv6 was to avoid that. So in theory, what IPv6 does is it sends to a group of addresses, which is small. It contains certainly the destination, but it might contain others. So we limit the damage by bothering only a small number of hosts. This assumes that I have an efficient way of delivering multicast packets. If it's true that I have an efficient way of delivering multicast packets in a local area network, in a way such that I send the message only to those who truly subscribe, the language for multicast address is, in order to receive traffic from a multicast address, you need to subscribe to it. That means the operating system needs to instruct the communication adapter that it has to receive those things here. So here, there will be a small difference in the sense that all the communication network adapters of all hosts will be instructed with their corresponding multicast addresses here. So C, the hardware of C, will decode the MAC address, but by looking at the IP address, we'll see, oh, that's not for me. And we'll perhaps a few microseconds before what we would be with IPv4, we'll be able to know, no, it's not for me. But that assumes a lot of things. It assumes that we are able to handle multicast way in an efficient way. Question?
Yeah, so like there's a mapping because like this packet is encapsulated in a frame, right? So there's a mapping between the destination address of that frame and the destination IP address structured in that way.
Yes. We'll talk about it when we talk about multicast, but that's a very good question. We see it here. We see that this packet here the solicited node multicast address is here. It's the prefix that's for solicited node multicast address, and the significant part is 01 column 1. This is mapped to a MAC address, which is also a special prefix 3333FF 01001. So we see we copy the part here in the MAC address here. So now that assumes that the bridges are able to handle those MAC addresses well. And if they do it well, then the packet will be delivered only to the communication adapters that subscribed to this multicast address. But what I said is that many switches and bridges don't do that. They just broadcast it to everyone, which limits the benefit. But that's how things are. What I'm trying to do in this course is to explain to you why things are the way they are, so that you can better understand and remember. I don't pretend that this is optimal, that this is how an intelligent design today would do it. But also very often the reasons that lead to such decisions are based on observations coming from many, many practical cases. Microsoft does this, Apple does that, Novel Network does this. So all those people were in the committees that decided on those, and they had reasons to do it this way. Now, this was standardized 20 years ago. Now, whether those reasons are still valid today is another story. My presentation of ARP so far is very naive in the sense I'm assuming that I sent a query, who has this IP address? And I believe that only the system that has this IP address will reply. Now, if you sit on a Wi-Fi hotspot somewhere, of course, you could use your Linux computer and in proxy way and receive all those queries and reply. So by doing that, you will be able to impersonate someone else. And if you're faster, if that someone else is faster, then you will lose. But if you're faster, if you have a very fast computer, or if you manage to have very good connectivity with a base station, you will be able to say, oh, that is me. And then all traffic that A sends to B, in fact, goes to you. Where, of course, you can do whatever you want with it. You can read it. You can forward it to B then by forging the MAC address of A. So B will not see that there is a problem, but you have mounted a man-in-the-middle attack. So that's very easy to do. And it's possible, and it happens. So where you're a Wi-Fi, public Wi-Fi station, probably this is possible, and probably this happens. So which means that whatever you send from A to something must be encrypted. So you should use a VPN, or if you're using a public hotspots, you probably should be aware of that. Now, of course, a lot of the traffic that we are sending, even if we're not using VPN, is encrypted. When I go to a web server, when I go to my mail server, hopefully you've used the TLS encryption so that the traffic that is seen here will be of little use, but can still be a bit used here. So that's a security issue, and it exists in every environment where you can assume anybody can have access to the local area network. One way to mitigate it is, of course, to limit the access to the local area network, which is what EPFL does, for example, on the wired network and also on the wireless network, because you have to show credentials. You cannot just know a password and connect. And this is complemented by what is called DHCP snooping and dynamic ARP inspection. DHCP is a protocol we'll see in a few more minutes that is used when you acquire your IP address. So when you come into the EPFL Wi-Fi, for example, for the first time, you get an IP address. This is allocated to you via DHCP. Now, DHCP is one function, MAC is another function, IP routing is yet another function, but very often they are all in the same box. So if those functions are in the same box, which is your Wi-Fi base station, for example, then that box knows everything. That box knows which IP address was given to you when you came into the network. And of course, it knows your MAC address because you've talked to the DHCP function. So that box knows your IP address and your MAC address. If someone else asks, what is the MAC address of this person here? Then DHCP dynamic ARP inspection means that it is the base station that will reply to the ARP question. So it will not, the job of the base station would be to broadcast it if it's IPv4, send it to this special group if it's IPv6. But what we can do instead is reply in lieu of the destination. So it will not allow all those ARP broadcasts to happen if it's a well-secured Wi-Fi installation. And it will therefore filter all ARPs, and or it can only allow the valid answers or even answer instead of the final destination because it knows all the IP addresses and MAC addresses that are in the local area. So many enterprise networks do such things. Low-end like home routers typically don't do it. And I think it's time for a break. After the break, we will discuss of a more radical method that uses some cryptographic means. Voilà, we do a break and resume at 1:15. We're ready to restart. We've seen that ARP is essentially insecure. That can be mitigated in environments where ARP is intercepted by the same box that can check whether the answers are valid or not. This is, I would say, the state of the art in securing ARP today. There is another attempt, which is not so widespread, but perhaps will become more widespread in the future, which is called secure NDP. Here I'm showing the very simple use of it. There are several variants. This is used in some enterprise networks, where the idea is here to use public-private key pairs. So a few words of that. Many of you know that. So in a nutshell, a private public key system is a cryptographic system where you have two keys. You can encrypt with one key and decrypt with the other. You can encrypt with the public and decrypt with the private or vice versa. And as the name indicates, the public key is public. Everybody can know it, and that doesn't leak any information about the private key. But the private key, you should, of course, keep it secret. And for example, if you encrypt a message by adding some text, so use it as a signature using the private key, anybody can verify your signature because the public key is public. But the assumption is that only you or only some system that knows the private key can be the legitimate, can have signed the message. So it is used for authentication. And this is typically what is done with secure NDP. Here, the idea is that the secure NDP assumes that the IP address A network prefix is 64 bits. If you do it differently, then that will not work with this version of secure NDP. And then the host part is also 64 bits. And then the host part is a hash of the public key of the host and some other information, in particular the IPv6 prefix. So here the host part is the one that starts at 1, 2, 3, 4, 1, ATB, F, etc. So this is the host part here. The prefix is well known. The prefix doesn't leak any information. That's the EPFL prefix of this subnet. And what is assumed here is that in addition, you create a key pair for B, public key, private key. Public keys and private keys often require some key distribution system, public key repositories, but here we don't need that because the assumption is that the host part, which would not be this one, of course, but a more irregular one, would be the result of applying a hash of the public key. Right? So you cannot choose the host part freely. It must be derived from the public key, and anybody can know the public key, so anybody can know also your host part. But if somebody asks what is your MAC address, then your reply to the MAC address will be signed by your private key. So if B is really answering this message, B has created its public IPv6 address has derived it from its public key, and it signs the message with the private key. So when A receives the signed message, assuming hash collisions are not possible, which is true if you have a secure hash function, then A knows with very, very large probability that it comes from a machine that has the private key that corresponds to the public key. So it must be B, probably. That doesn't prevent someone else, like C, to do the same. So the attacker could send you a bogus message, but not a bogus message for B's address. The attacker could give you, because anybody can create their public-private key pair, but then it's your responsibility if you decide to go to this specific IP address, which is that of the attacker. If you know, you have a good reason to know that B's address is the one you want to have, because you've had it from the DNS, for example, and if the DNS is secured, then you will have some very strong guarantee that whom you're talking to, who sent you this reply with the correct MAC, with the MAC address, is somebody who knows the private key of B. This is the secure NDP protocol. It is only secure if the hash version is secure. Now, the first version of NDP used SHA-1, which is not safe, so it can be broken. So, but there are new versions that are being done. And as I said, some enterprises use this mechanism, but it's not quite widespread. At EPFL, for example, we don't use it. We mentioned several times DHCP, host configuration. Let's review in detail what it means. IP is very different from the MAC layer in the sense that it's heavy and requires a lot of configuration of an IP address, of an IP interface. So a host that has, for every interface that it has, it must know, of course, the IP address of this interface, the network mask, but also the IP address of the default router, and also the IP address of the DNS server, at least one DNS server. So the last thing is perhaps not so much of a problem because there are public DNS servers like 444 of Google, but not all companies allow you to go to some DNS server that is not inside your company. So in principle, you need those 4 things. That can always be done manually. And in the lab, you learn how to do that in your Linux machine, or in Windows or Macintosh, it's even easier. You go into the correct panel and you, by ticking on the right boxes, you will be able to fill in all those entries. But of course, this is a pain. You come to EPFL in the morning. You don't want to have to fill in all that stuff. So this is done automatically by a protocol that's called DHCP. That's the default protocol. With IPv6, as usual, IPv6 once has opened the box of complexity. So IPv6 always has different ways of doing everything, which makes it unnecessarily complex. So IPv6 has also Slack and stateless DHCP. We'll say just a few words about it. There are variants of that. For example, when your home router connects to Swisscom or to Sunrise or to whoever is providing you the service, it also receives an IP address. It doesn't use DHCP, but something which is particularly the same. That's called PPP, and or DHCP with prefix delegation that we will discuss in a few more minutes. So they're all variants. The name of the protocols are sometimes different, but the goal of those protocols is always the same: obtain those 4 elements that are required for IP to work. How does DHCP work? Here, for a change, let me start with IPv4. Well, it's very easy. When a host comes, for example, you come to EPFL and you connect to an Ethernet socket, or more likely, you connect to Wi-Fi, then you must, at the beginning, you don't have an IP address. So you must acquire one by sending a message, which is sent to what is called a server, a DHCP server. A DHCP server is a function. At home, for example, it is in your home router. At EPFL, it is on a dedicated machine that says what blocks of IP addresses are allowed. And also, perhaps, you can test that in your home router. You can say that some specific machines must have some specific IP addresses. For example, if you have a server at home, you would like that this server always have the same machine, the same address, even when the server reboots and asks for an IP address. But most of the time, in particular, if you come with your mobile to EPFL in the morning, you don't care which address you will receive. So you will receive whatever address the DHCP server has available for the next person who comes. Now, of course, there is a chicken and egg problem. How can you contact the DHCP server if you don't have an IP address? Then it's not possible. But it's possible at the MAC layer. So the trick is to put the DHCP server in the next hop router, or in the Wi-Fi base station, which is where the next hop router might be, by the way. So one way to do it is to have it in your next hop router. And then when you come into a local area network, with IPv4, you can send a broadcast and say, who is a DHCP server and would like to give me an IPv4 address, which is exactly what you do. So you send a DHCP packet, which is a UDP packet, but the destination IP address is IP broadcast, which works only for IPv4. And remember this all one address. In hexa, that would be FF everywhere. In dotted decimal, it's 255 everywhere. This is a local, an on-link address. It will never be broadcast beyond the local area network. And it goes to a port number, 67, which is the port number of DHCP servers. So if there is a DHCP server in your next hop router, it will receive this message and will reply to you by looking at your MAC source address, and will send you a message to your MAC address with the address, the IP address that you're looking for. That is, if you put the DHCP server in your router, which is what you do in small installations, like in a home router for an apartment. At EPFL, we don't want to do this. So, and we don't want to have, there is 1,000 base stations at EPFL, so we don't want to have to configure 1,000 DHCP servers. So what you do is you have a single DHCP server, perhaps duplicated for reliability. We want to be better than Facebook. And then we put here a function that is called DHCP relay. A DHCP relay formally is an application layer intermediate system. It's a system that understands this is a DHCP message and forwards it to the DHCP server. So this one will receive all this message. It listens to port 67 and it will receive it because it's broadcast. So everybody will receive it. So in particular, this one will receive it. And then this is in a function inside the local router. So it is well configured with an IP address and everything. So it will simply forward it to the DHCP server that will do the job and will reply. And while forwarding it, it will add all the information about whom it came from, on which interface, and on which MAC address, so that now it receives the reply. Please give this IP address to this person that contacted you, and it will do the job. So we find here, the idea is very simple. In terms of terminology, this is a bit confusing. In particular, this is where the layered approach that is presented so cleanly breaks a bit in multiple places. We've seen NATs break it a bit. Yeah, this is another place where a router that in principle is something that acts only on IP packets. Well, in fact, this function is inside the router, but it's not a router function. It's a DHCP relay function that replies to UDP port 67. So it's truly a little application that's running. Of course, there's this number of bells and whistles when you, in any particular, DHCP addresses acquired in this way have a certain lifetime. So once in a while, when the lifetime expires, there will be an attempt to renew the lease of the address. This is to make sure that once you give, if you give an address to this machine and the machine dies because you change your smartphone, for example, then you don't want to block this IP address forever. So this address will disappear and will be considered free again by the DHCP server if it is not regularly renewed. In IPv6, of course, we can do the same, but since, as you can guess, we will never do a broadcast. But other than that, it's easy to imagine what will be done. Except in IPv6, there is something radically different, which is called auto-configuration, stateless auto-configuration. Stateless alludes to the fact that there is no state. No state means there is a record that's written somewhere and survives crashes, for example. Here, the state is the DHCP server. The DHCP server has a table that knows which address is for whom. Stateless means without server, more correct name would be serverless auto-configuration. And this was justified by the competition. In the 80s, there was IP. It was very clumsy to use. Only people in universities were using IP. People in the real world, if they were fancy, they were using Macintoshes. Apple Talk was completely self-configured. Nobody in Apple Talk ever had to fill in an IP address mask and things like this. People did not know. The way Apple does is to hide all the complexity to users, so they did not even know. And it was possible to have a Macintosh, deploy several Macintoshes and a printer in your local area network, and that would magically work. There was no configuration to be done. With IP, it did not work at that time. And we wanted to imitate this. In particular, one thing that you need to do is allocate an IP address. So your machine boots, you want to allocate it an IP address. If you have a small configuration with only a printer and 2 or 3 devices, you don't want to have a DHCP server and so on. Now, today, people don't really care. You probably have a home router that has the DHCP server for you. But if you want to work without a home router, which is a bit difficult now, you will learn to do it in the lab. You will learn to connect 2 PCs together, for example, and make everything work. But believe it or not, with Macintoshes and Apple Talks in the 80s, it was very easy to do. You just pull the wires between the machine and it would do it. IPv6 imitated this. Apple Talk has disappeared. Now it doesn't exist anymore. It's the Macs do everything over IP. But IPv6 has imitated this by what is called auto-configuration. And also IPv4, as we will see later, imitated it. The idea is simply to obtain an address automatically by first having what is called a link local address. So IPv6 always does that, whether you use DHCP or not. So the first thing a host does when an interface is activated, or when the host boots typically, is to obtain an address which is called link local. So no, sorry. By having the host part derived by one of many methods, and in fact, many systems like Macintoshes will use 2 of those methods. Will use this one, the secure autoconf address that we will give here. So here, for example, we will assign the host part randomly. There are other methods that are used, for example, in Linux systems, which are to obtain it directly from the MAC address here. So if you have a MAC address is 48 bits, and you need a host part of 64-bit, that should not be a difficult problem. Every MAC address can give you a host part because there's more bits here. Now, when you do this, you obtain your address, you do an address duplication test by sending, if it would be IPv4, we would send a broadcast. If it's IPv6, we send a multicast packet, and you can guess this multicast packet is sent to the famous solicited node multicast address that is derived from the address that you want to acquire here. If no one else has this address, no one will reply to this duplicate test, so you consider it's fine, and you obtain this. Now you have a linked local address. Linked local means an address that's usable only in the local area network. Probably you will, and if that's all you have, if you have your 3 Macs and a printer, that's all you have, end of the story. So you have your IP addresses. The printer also has one, all the hosts have one, so everybody has an IP address and everybody's happy, most of the time. Now, if you want to be connected to the internet, there must be a router somewhere. So you can then send a message to all routers by asking, is there somebody who is a router in this local area network? By sending it to the multicast group that contains all routers. And if there is a router that agrees to send you a reply, this router can send you the information about the network prefix. What is the prefix and what is the network mask? The router must know that to do its router job. It must be configured and know it, so it can send this information to you. So by this method, you will receive an address with the correct prefix, with the correct network mask, and with a host part that is unique in this local area network, at least as unique as is possible by this test. Question? So the question is about the use of multicast address. For example, here in the duplicate test, we see that we have to send a multicast query to the group of all people who respond to the solicited node multicast address of my address, the one I'm trying to acquire. So the question is it necessary that all machines subscribe to those multicast address groups? And the answer is yes. If you do a valid IPv6 implementation, and of course, you can do your own. You can fork a version of Linux with your own IPv6 implementation, but probably there will be a few people, if you do it open source, that will complain about the fact that you don't do it right. So it's part of the mandatory things of an IPv6 implementation to subscribe to its solicited node multicast address of all the addresses that it belongs to. And if you are also the all hosts, and if you're a router, also the all router. So this is how Slack works. Now there is a problem with IPv6, exists also partly with IPv4, but is more dominating with IPv6. Remember, if we use IPv6 at home, probably my home router will not act as a NAT. That means my IPv6 address that I have at home is visible to the whole world. And it's intentional. That was the design. IPv6 was made with the idea there's an IP address for everyone, and the network, the IP principle says one IP address for every interface. But of course, the reality is a bit different. And in particular, the world is more hostile than those principles assumed at the beginning. It might not be a good idea that your address is visible and remains the same always. That makes it very easy for external services to track you. Whenever you connect, it's very easy. You have a cookie in your address, right? So you are giving to everybody who you are, and by a few other information that you can compare, it's very easy to find who you are in reality. So your IP address with this system signs who you are, really. And worse, if you use, for example, the hosts, the IP address that's derived from your MAC address, if you are using Wi-Fi, and you go from IPv6 Wi-Fi to IPv6 Wi-Fi, you always have the same host part. So you're assigning who you are everywhere. So you're sending that cookie to everyone. If you want to avoid this for privacy preservation, then there is an alternative, which is the secure autoconf address, which computes. So one way is to compute a truly random address that would change all the time. But the problem with that, it's a bit heavy on the system. So this is a solution that exists. So some systems deploy that. So the temporary random address means that you acquire an address with Slack, and you change the address once in a while. So if people are trying to track you, then they will lose track of you because your address changes every 24 hours, for example. That's the principle. Now, it has an interesting side effect. That means that contrary to IPv4, with IPv6, we should be expecting that the same interface might have many, many IP addresses. For example, because it changes its address every few hours. Now, if you change your address and there was a long-lived TCP connection, you were connected to something that sends you a keep alive mechanism every few minutes, you don't want, if you declare the old address to be invalid, you will break the TCP connections, which might not be desirable for many applications. Will complain about that, will reboot or restart some processes. So if you want to keep your address, that means that you will have, for example, deprecated addresses that are very old, that you don't use anymore, but that you continue to use because you started them several days ago, for example. So the same physical interface on IPv6 will have, because of that, multiple addresses. Not just because of that. If you remember my previous slide, the first thing that an IPv6 host does, if it uses Slack, is to get a linked local address, an address that works only locally. Plus, if it's connected to a router, it will get another one. So it has already 2 addresses. If it uses random addresses, it may have even more. There's a variant of that, which is called secure autoconf, that also randomizes the address, but in a way that depends deterministically on the subnet ID, which by having a cryptographic hash applied to the number of things, a secret key, and the subnet ID, the secret key will make it random. Then this will give you an address that cannot be guessed because your secret key is a random sequence of bits that is, for example, given to you when you install macOS, because macOS is using that, for example, here. Then your address will be completely unguessable, so it's impossible to know who you are. And whenever you change subnets, if you go from one place to another, you will have another address. So tracking will be more difficult. But as long as you stay in the same subnet, the address will be the same, which means if you have connection with servers, for example, you will not need to change addresses like you do here. So that is things that is done, for example, on Apple systems, and this is often done on Windows systems. This is the basics. Sorry, this I said. DHCP, we've seen it for IPv4. DHCP works in practically exactly the same way with IPv6. So with IPv6, you can do automatic configuration, then you don't use DHCP. Or you do DHCP, which is very similar to IPv4 with the obvious changes. We don't use broadcast, we use solicited node multicast addresses. Except if you do Slack, you don't get the 4 items I mentioned. You get your IP address prefix, and the network mask, and the mask, your address and the mask, therefore the prefix, and your router default address. You get that from the router if it exists. There's one thing you will not get. It's the DNS server interface. So you could say the router could give it. That's an option. But if your router does not, there's another option, which is called Stateless Dhcp. That means after doing Slack, you can still go to a DHCP server, but with the only purpose of asking what is the DNS server IP address that I should use. So you see that in the tree of all the complex things that we can do, IPv6 allows all of them to happen. So if you install IPv6 at EPFL, for example, which we are doing now on the IPv6, the EPFL network is doing now on the wireless network. They started with Slack and Stateless Dhcp, and then they found out, well, it's not so well with Windows machines, so now they're doing a DHCP. So IPv6 has a complexity because so many things are possible, and it's not always easy to know what you should do. Yet another variant, this is, for example, done on Android systems, is called DHCP with Prefix Delegation. That's a small variant of what we've seen before. If I am, for example, my home router, if I receive an IP prefix, we said that my provider will give me an IP prefix. However, if I do that, I have the prefix of my router, that's an IPv6 address that is given to me by Swisscom, for example. Then I have my own local area network in which I have multiple prefixes. I can have multiple subnets. And if I do it the way I said here, I will have in the routing domain of my provider, I will have two prefixes to give. I mean, two routing tables, one to know that corresponds to my IP address, and another one that corresponds to all the prefixes I gave here. So the way, and in order to avoid that, we give a prefix to my home router that contains the IP address that is given to me by the public provider. But of course, I am forbidden to use it, to reuse it internally. So this address here, that is given here, is part of the domain that of the delegation that I've received, but is excluded here. So this is how DHCP with prefix delegation work. So the prefix includes the prefix of the link from ISP to the system that is given to me. So this is very often how things are done in mobile networks. In mobile networks, you will have multiple IPv6 addresses. For example, if you use your mobile phone to as a Wi-Fi hotspot, it's called tethering. You can, or sharing connection in Apple's terminology, tethering in Android's terminology. So this becomes a router between the cellular network and the Wi-Fi here. And then you need to have multiple devices that will receive IP addresses. This is all possible because with IPv6, we have large prefixes. Question?
Yes. So since an ISP allows address match or set of address matches, what happens if the server somewhere doesn't respect that address match and finds the MAC address outside of the ISP? What happens?
So the question is, what will happen if the DHCP server here allocates an address that is not in the range that has been given to you? Right. So that is exactly what will happen if you come to EPFL, you configure your machine with an address that is not an EPFL address here. Well, the first thing that will happen is that any packet that comes to you will not reach you, because the routing of the internet will never send those packets to you. They will send it to somewhere else, to what corresponds to this address. Right? So it's like if you order something online and you give us postal address, someone else's postal address. Right? The parcel will go somewhere else. Perhaps you want to do that, so the denial of service attack. Perhaps you want to do that, but that's certainly your system will not work. Question?
Yes. So, like, first one with SLAC, we assume that the network mask is 64 bits, right? Because we say that the host part is 64 bits.
No, with Slack, we first receive a link local address where the host part is 64-bit, but there's no prefix in some sense in the link local address. It's a FE80 prefix that is always the same. It means link local. And then the host part is 64, correct. And if you work only in the local area network, if you're not connected to the internet, that's all that will happen. But if you're connected to a router, you will speak to this router using your link local address, and this router will tell you what is the subnet mask that you should use.
But by link local address, you mean like an IPv6 address which is local, or you mean like a level 2 address?
No. So the question is what link local means. So link local address, we've seen that already with it exists with IPv4 and IPv6. A link local address, link local is a synonym for inside subnet only or inside local area network only. But it is an IPv6 address. It's not a MAC address. It's an IPv6 address. There are also IPv4 address, the 169, etc. So those are link local addresses. That means that this address is meant to be used only for systems that are inside the same local area network, which concretely means a router never should forward a packet to such a destination address.
And how should I then reach, like to reach the router, I auto-sign my address, right?
To reach the router, so when you're in the discovery phase, then you send to the multicast address of all routers that are on link. By the way, link local is a synonym of on link. In old days, link layer means MAC layer. It was the same. So local area, link, those are synonyms. So link local means on link, means scope, that is local area only. But those are IP addresses. In IPv4, the 255, 255, 255, 255, that's a link local address. It's a broadcast that is link local. Well, here is an example here. Here I have examples of link local addresses. For example, FE8001, that's the link local address of this router, of this north interface of this router, which of course is not very useful. If I want to reach this router from far away, I need its global address, which is this one here. And very often, but not necessarily, if the prefix is 64 bits here, if the prefix is 64 bits on both, then they will have the same 64 bits, which are zeros and ones here, but not always here. In particular, one of the things that IPv6 is doing, because in IPv4, a link local address is a rare thing. You use an IPv4 link local address when you are in the scenario I mentioned before. You deploy your machine out of the box. It wants to connect to your DHCP server, which is in your home router, but there is not. You connect your printer to a laptop, for example, or you do an ad hoc network in a room with a few friends. You want to connect to each other and you're not connected to the rest of the world. Then when you boot your systems, which IPv4 address will you use? Well, you will use those link local IPv4 addresses, exactly like Slack by doing duplicate tests. I don't do it for IPv6 IPv4 every time because it's boring. It's always the same. As you can imagine, the duplicate test is not sent to the solicited node multicast address, but it's sent to broadcast. Other than those little subtleties, it's exactly the same. So with IPv4, you will have your machines that can work, but that's very seldom done. It's only done by Windows, as far as I know. Macintosh will give up and say, oh, I'm not able to work, which is surprising because with Apple Talk, they were able to do it before. And Windows will do it. Windows will try to find an address, do the duplicate test, and it will be able to work with another machine in your environment. But that's extremely rare. Most of the time when you deploy a machine today, there is at least a base station, a Wi-Fi or home router or something. So this is rare in IPv4. In IPv6, it's the rule. You always have your link local address plus others. And in IPv6, very often the rules are, if you talk to someone that has several addresses, so A talks to B using IPv6, A knows the IP address of B. If you know several IP addresses of B, a link local and a global, and if you're on link with B, on link means on the same local area network, then you should use the link local address. It's one of the principles of IPv6, which means, for example, good or bad, I'm not sure, but this is one of the practice that are done, which means that in the routing table, when we say the next hop, for example, we will give the link local address of the next hop. So for example, in the routing table of this router, the next hop for this, or the default of EPFL, will be this address, FE80 : 1, which of course does not indicate to this router which interface it is, because on the north interface, it has another interface that has the same link local address, right? Because the rule at EPFL is that the default router on a subnet have the host part equal to 1. Very easy. Many systems do things like this. So the host, the link local address of this router will be FE80, lots of zeros followed by 1. And same address here, which is okay because a link local address is link local. It is meaningful only inside the local area network. In order to go from here to here, you need to cross a router. You're not in the same local area network. That's one of the particularities that you should not be confused with in IPv6. That will happen. Of course, in the routing table, you want to make the difference between this address and that address, because the next hop when you go here is the same address. So therefore, we add an interface number in some form. The next hop is not fully qualified by its IP link local address, of course, if you are a router that has multiple interfaces here. In contrast, as I said, usually with IPv4, there's only one IPv4 address per interface. But of course, a machine typically has multiple interfaces, but a given interface has only one IP address here. Okay. This is what I just said here. Let me skip those things. This is what I mentioned for the link local IP addresses. And let's move to the little question. When an IPv4 host uses DHCP, which of the following information does it acquire? I close the poll in a few seconds. And as you can see, the correct answer is D. With Slack now, what's the corresponding answer? I also close in a few seconds. And as you can see, the answer is A. All right, let's move on to the last topic of this module, which is the time to leave. There's other fields in the IP header. Most people will call it time to leave. The real name is hop limit. And what's the problem? Well, in IP, we believe that the routing tables are correctly set. And we've seen with Facebook, if this doesn't happen, then everything breaks down. But the smart way of updating the stupid way of updating the routing table is to go via SDN into every router. But there's a chicken and egg problem. How do you go into a router if there is not a path to go to this router? So the smart way to do it is to use distributed protocols that we will discover in the module about link state routing. But one side effect of this is that you cannot guarantee perfect synchronization. If I have a network with 200 routers and I change a route somewhere, instead of going this way, it goes that way, the time at which this change is implemented might not be exactly synchronized. We cannot download all the routing tables and have a global synchronization protocol with PTP in all routers and say, cling, at this time now change the routing table. We could do that, it's a bit science fiction. In reality, we don't do that. The routing tables are changed, and hopefully the time difference is not very small, is not very large. But while the things are changing, there can be inconsistencies in routing tables, and inconsistencies in routing table cause loops. It can be that, for example, A sends my next hop is B to a given destination, and B sends my next hop to the destination is A. If I do that, the packet will do a ping pong between the two. Well, is it bad? Well, if that's a transient thing, we might not care, except if remember, propagation versus transmission time. If we're in a system like this, where essentially the times are short, such that the time it takes to send a packet to B. So A sends a packet to B, and if the propagation time is short compared to the time it takes to the transmission of the packet, then B will send it back almost immediately, and A will send it back again. This is a single packet here. The pink area means the channel is busy. So you see that a single packet will make your link fully busy. If the propagation time is very large, perhaps a second packet could sneak in, but that doesn't change. Instead of having one packet that blocks the link, there would be 2 or 3 packets that would block the link entirely. So take-home message here, if there's a routing loop, it just doesn't mean that your packet is hanging around and circulating, but it means that your packet is doing a denial of service attack on your link. The link cannot be used. It's busy transmitting one packet, or perhaps 2 or 3. So that brings the link down, not just the path from A to B. Now, if there is, due to some bug in software or bug in configuration, there's a routing loop, then that brings the thing down. How is that avoided? By having what is called a time to live. If a packet, whenever a packet is transmitted by a router, there is a field in this router called time to live in IPv4, time hop limit in IPv6, that is decremented by 1. It starts at some value, which is 60 or 64. And whenever a packet goes from A to B, then it is decremented. And when it comes to 0, the packet is declared invalid. And therefore, the packets will loop here, but only for a small finite number of times, which will limit the damage caused by, I will steal 2 minutes of your time, that will limit the damage caused by those loops here. And we have used this. We have used this feature. It's called time to live because at the origin of the internet, it was truly a time in seconds. Imagine we're in the 70s, a packet would take 1 second to go from one hop to the next. And the time to live was really a time in second, and we were supposed to measure time. Now, of course, at the speed things are happening. One, we don't want to measure the time spent by a packet. That would be a very difficult task to do it for all packets. And second, the time would be much smaller. So now it's really a hop count. And how does traceroute work? When you traceroute this destination, for example, in fact, you send a packet with TTL equal 1 or hop limit equal 1. TTL equal 1 means I send this packet. When it traverses a router, then it's decremented, so it's killed. So if the destination is not on link with me, I will not reach it. But the destination is not on link. So it will go through a router. And there is a thing that, in principle, routers do. If you are a router and you send the packets and you go through your routing table and you're forced to kill the packet because the TTL has expired. Packet is too old. You have to kill the packet. Although you have a correct destination, then that's an error case. There is a loop somewhere, presumably. So you send an error message back to the source, sending there is a problem here. An error message means an ICMP message. Not all routers do that. Companies like IBM don't do it. So if you go into IBM and you send this, they will never send, or many companies don't do it, but many internet service providers do it. If the routers do it, then whenever I send a packet to this destination with TTL equal 1, the first router will complain and will reply to me, error, time to live expired. But by receiving this complaint, I can know, oh, this is the first router on the path to the destination. And then I go to the DNS to find what is the name of this router and I print it. And so on. Then I increment, I send again a second packet with TTL equal 2, and then the second hop on the path will complain and I will send that, and etc. And this is how, if that works, this is how I will discover the path, or at least one path to the destination. Sometimes we don't get correct answer, we get stars instead. That means all the routers that are here, they don't reply. They silently drop the packet, which is what many commercial networks do here. Voilà, I think this is, that's all for today.